everyone. Welcome to the next session of Strength of Material. Today I am going to deal with the topic shear force and bending moment. First we will talk about the types of beams. The first type is simply supported beam. You can see over here AB is a beam. It is supported on both the sides by two reaction forces VA and VB. So this will be called as a simply supported beam because it just has two supports. The second type is called as simply supported beam with overhang. In this type of beam, you can see that ACB is what I have marked over here, out of which AC is the beam and C to B is the overhang portion. The length of the beam is L and A is the overhang portion. This is labeled as single overhang on the right side because AC is the beam and you can see that CB is the right hand side portion of this beam. In the second figure, here you can see C to B is the beam. At C and B, you can see two reaction forces. L is the length of the beam. A is the overhang portion. This is called as single overhang on the left side because the overhang portion is to the left of the beam. In the third figure, here you can see CD is the beam, A is the overhang portion and B is also the overhang portion. There is one overhang to the left and one overhang to the right, hence the name double overhang on both sides. The third type of beam is called as continuous beam. Here you can see A, B, C, D as the complete beams. Here I can say A to D is the beam portion. At A, B, C and D, you can see there are four reactions, which means it is supported at every point of the beam, hence it is called as a continuous beam. The fourth type is called as cantilever beam. Here AB is the beam portion whose length is L. At end A you can see it is fixed and at B you can see it is free. So any beam which is fixed at an end and free at the other end is called as a cantilever beam. The fifth type is called as fixed beam. A beam which is shown over here, say I call it as A and B. So AB portion is my beam whose length is L. When it is fixed at both the ends, it will be called as a fixed beam. So these are the five types of beams which are possible. Next we will talk about types of loads. The first type is called as point or concentrated load. Every load which is concentrated at the point over here is called as a point or concentrated load. You can see F1 and F2 both are called as point or concentrated load because they are acting at a particular point and they are concentrated over there. Here F1 is directly a vertical force. F2 is not a vertical force, it is an inclined force. It is acting at an angle theta with respect to the horizontal. Based on the first year's concept which you have studied in engineering mechanics, this force can be resolved as F2 cos theta and F2 sin theta, and that is how the numerical can be solved. AB is the beam. At A there is a reaction VA, at B there is a reaction VB. VA and VB are also point or concentrated load. Point or concentrated load is something that we do not prefer in nature. The reason is because it is going to create a wedge kind of action at the edge where it is acting upon, or it is just concentrated at a point. So I can say that when there is excess amount of load at a point, the pressure will increase, which will lead to the increase of stress on the beam. So this is not something which is preferred or what you want to have. What you preferably have is called as a UDL or a UVL. So we will talk about the next type, which is called as UDL or uniformly distributed load. It is also called as rectangular load because of the shape. As you can see over here, the shape is of rectangular type. Okay, we will first take this figure. Now for resolving this UDL into its equivalent FBD, I will first draw the beam which is A to B. At point A, the reaction is VA. At point B, the reaction is VB. Now I have to resolve this force, which is of W per unit length, and it is acting over a length L. So for resolving this, I am going to talk about a rectangle. So when I say it is a rectangular force, a rectangle can be shown in the form of a point load. When you resolve this entire area and you mark it as a point, so for example, if this is 2, as you can see, the height over here is 2 and the length is 2, the area will be length into height, which will be 2 into 2, 4. Similarly here it will be W into L. So that is the load, because it is W per unit length into length. So the total value becomes W kilonewton or W Newton, whatever is the unit of W. Now, where does it act? Which is a very important point. If you recall the concept of CG, which is center of gravity, for a rectangle, suppose if I draw a rectangle here, if I have a rectangle, this CG is always at the center. Or I would say if the length over here is 2 meters, then the CG will be at 1 meter. And if this height is also 2 meters, I can say that this distance will be 1 meter. So it always acts at half of the two edges. So obviously it should be acting at half here as well, because this is a rectangular load. So W into L is the total value, and it will be exerted at half of this length, which is L by 2 from both the ends. So this is how a UDL, uniformly distributed load, is supposed to be resolved. Now I'll solve the numerical which I have taken over here. I'll just project the points. It will be very easy to draw. I projected the points. I just draw the beam AB. At A there is a reaction VA. At B there is a reaction VB. This distance is 1 meter, and this distance will be 1 meter. Now CD portion has to be resolved because it is a UDL portion. So here I will multiply 2 into 2, which is 4, and it will be exerted at half because it is at CG. So I'll mark over here 4 kilonewton, because this is meter and meter. So when you have 2 kilonewton per meter multiplied with 2 meter, obviously this meter gets cancelled and what remains is 4 kilonewton. So this is what I have written over here, and this will be exerted at half, which is 1 meter distance from both the ends. So this is how a UDL is supposed to be resolved. This is a FBD of this load diagram. So what was given to me was the load diagram, and this is the FBD that I have drawn. FBD is free body diagram. Next I'll go to uniformly varying load, UVL, or it is called as triangular load. It is called as uniformly varying load because you can see this is the beam AB. Over the beam AB, when I walk from A to B, I can continuously see that the load is of increasing type. Here it is also called as triangular load because it resembles the shape of a triangle. So if I have to draw its equivalent FBD, I'll first project the points. I'll draw AB. At A there is a reaction VA, and at B there is a reaction VB. So this file is not written. Let's say W per unit length, like I had taken before. So suppose if it is W per unit length, if I have to multiply, how do I multiply? If I have to calculate the area for a right angle triangle, what I am supposed to do is half into base into height. This is the formula. So here half, base is L, and height is W, which is the maximum height which is to be taken. So this will be WL by 2, which is my load value. Now where do I place it? Again, for a triangle, the CG will lie at 1/3 from the heavily loaded end. It is generally set from the base, but when you have a triangle like this, it is very simple for you to mark the CG, because you say 1/3 from the base over here, L by 3. Say this height is L. So you can just say it is L by 3, which is very simple. But here I cannot say that from the base, because here this is suppose the base, which has now become the height. The height has become the base. So what I'm supposed to do is I'm going to use a very simple term so that I can use it commonly for both the situations. So suppose if I say for this situation or for this situation, I would say that from the heavily loaded end, I'm going to mark the CG at 1/3 distance. So here, this is a heavily loaded end. So from this end, I'm going to mark at 1/3 distance. So total length is L. So I will mark it as L by 3. And at L by 3, my load will be WL by 2. And the rest of the distance is 2L by 2. Here also, if you want to say, this end is obviously heavily loaded because here the value of weight or mass is going to be more. So from this end, it is L by 3. So for both the cases, this statement will hold true, and this will help you remember for both the cases. Now this is one type of uniformly varying load. There is another type which looks like this. This is of decreasing type, so this looks like this. So you can just draw for the same figure. I leave this as an exercise for you. So if you have a decreasing type of UVL, you can draw the similar FBD for it. Okay, so this is all about the types of loads. Next we will go to types of supports. The first type of support is called as a roller support. You can see over here, this is called as a roller support. So suppose if I have to draw the FBD for this, I will just draw the beam first, A to B. The length is L. Now for roller support, there is only one reaction which will be called as VB. Here I am going to use a symbol V. V stands for vertical, and suppose if I have a horizontal force or reaction, I would say it is H. VB is the reaction. Now what do I mean by reaction? Let's take an example of a roller. You all must have seen the sliding doors, which are very much prevalent these days on the window, or you can have a door which is of sliding type. So at the bottom portion, you must have seen which is something which is called as a roller, which helps the door or the window move very fast. So if you imagine that roller, if you think, is the roller able to move in the X direction very freely? Yes. Is the roller able to move very freely in the Y direction? No. Because you do not move the window in the upward direction. You just slide the window, say along the X-axis or Z-axis. Now I'm not talking about a three-dimensional figure, I'm talking about a 2D figure. So that is why I will not say Z, or if you say Z and Y, it's absolutely correct, or I would say X and Y. So in that case, if I say that the roller is moving only in the X direction, so it is free to move, which means there should not be any constraint or any reaction in that case. Hence there is no horizontal reaction. The roller makes it constrained for the window or the door to move in the y-axis. Hence there is a reaction which comes along the y-axis. Similarly at point A, here you can see, suppose if I have a roller or if I have a hinge at this point, I can show a reaction which will be VA. Okay, now I just assume this is a roller, which is not actually possible that you'll have roller, but for a beam, let's leave it to this. We will go to the next one, which is called as a hinge support. I will redraw this beam AB. The length is L. This is a hinge support, this is a roller support. As I told you, at point B, since it is roller, you are going to just draw one reaction, VB. Now when I talk about a hinge, let's take an example. We are all aware about the hinges which are prevalent on the doors. So if you try to move the door in the x-axis, you just want to pull the door towards you in the x-axis, it is not possible. The door is free to swing. Please understand carefully, the door is free to swing. I'm not talking about swing, I'm saying you hold the knob or the handle of the door and you try to pull it towards you. You just want to break it and bring it towards you. It is not possible. The door is hinged. It is kind of not allowed to move along the x-axis. Similarly, if you hold the door and you want to uplift it in the y direction, it is not possible. That is not the kind of movement that we expect from a door. So, for a hinge reaction, the object is constrained to move along the x and the y axis both. But it can swing. Hence, there is no moment reaction here, but there will be one reaction in the vertical axis and one along the horizontal axis. So this is my equivalent FBD. Now let's talk about a fixed support. When I talk about a fixed support, how do I draw this? I'll first mark the beam AB. Say at point B there is a load as it is shown over here. The value is not relevant at this moment. We are not concerned about it. The length of the beam is L. At point A, you can see it is fixed. The symbol is used for fixed. For fixed, if you talk about the frame of the door, a very good example, a frame is a rigid support and it is completely fixed. If you try to pull the frame towards you in the x direction, it is not possible because it is fixed. It is constrained to move. So there will be one reaction in the horizontal direction. It is also constrained to move in the y direction. Hence the frame doesn't move in the vertical direction. So it is constrained means there will be a reaction V. Also the frame cannot swing from side to side. This way, it cannot swing. So obviously there is a moment as well which will be called as MA. Hence there are three reactions for a fixed support. For a hinge there are two reactions and for a roller there is only one reaction. So this is something which needs to be remembered and recalled as and when we solve the numerical. So this is all about types of supports which are important for studying SFD and BMD. Next we will talk about a very simple concept which is called as statically determinate beam. We are all aware about the Newton's second law of motion, which is summation of force in any direction is equal to rate of change of momentum in that direction. I am talking about any direction x. You can talk about the direction y, z or any other direction. In this formula, which is the Newton's second law, if I say that the body has come to a halt or the acceleration has become zero, mass can never be zero, please mark that. In that case, I can say that summation of force along any axis is equal to 0. This is called as D'Alembert's principle. Now, this is also applicable to a force in y-axis. There is also another equation which you see over here, that the summation of moment will also be 0. Now, this is obvious. When you say the summation of force is 0, which is equal to m into ax, you can say that summation of moment is also going to be equal to 0 about any point in that body. These are the three equations which are a part of D'Alembert's principle. If we can use these three equations to solve any beam problem which is given to us, then the beam will be termed as a statically determinate beam, which means that the beam is in static state. So I am saying statically. Determinate means you are able to determine the unknown values of reaction, and we are obviously going to study a beam, hence it is called as statically determinate beam. If using these equations I am not able to solve the reaction values, then I will call the beam as statically indeterminate beam. The term in gets added here to the word determinate. It becomes indeterminate, which means you cannot determine, you are not able to calculate the unknown reactions. So this is a very important concept, and with this I conclude this session. I hope you have understood the basics of this chapter, SFD and BMD. In the next session we will talk about these terms, SF and BM, what are the sign conventions, how you are supposed to draw the shear force diagram and the bending moment diagram. So I will see you in the next session with some new concepts. Thank you.